Today I'll be doing the first practice problem for homework number 7. To restate the problem, and as I restate, I'm going to draw the problem as well. So we have a flat plate, and we have engine oil that is flowing over this flat plate. And it is flowing over both sides of the flat plate. That's an important detail because we will be developing boundary layers on the top and the bottom of this flat plate. Okay, we know that the length, this is a plate with a finite length of 1 meter. We also know that the engine oil has a temperature of 100 degrees Celsius. The plate itself has a surface temperature of 20 degrees Celsius. And we know the speed of the engine oil, which is 0.1 meters per second. Let's go ahead and write that it's engine oil. Okay, so we've restated and drawn our problem. Usually we also like to draw an energy balance. Here I'm just going to draw a little differential control volume inside of our boundary layer. I'm doing that because today we're using a lot of correlations, all of which were derived by doing a momentum or energy balance on a tiny differential control volume. Okay, let's talk about the things that this problem wants us to do or find. So the first thing is it wants us to find the thickness of the momentum and thermal boundary layers at x equals L, where x starts at the leading edge. So we're asked to find the thickness of our boundary layers at the trailing edge, right there at the very end, for both our momentum boundary layer, and again, we'll have a thermal boundary layer. Because it's engine oil, we know that they will be a fairly different thickness. We'll see just how different soon. Also, we were asked to find the heat flux at x equals L and the shear stress at x equals L. Okay, finally, we are asked to find the total drag on the plate per unit depth in and out of the board, and the total heat rate, the total amount of heat going into the plate, since T infinity is hotter than Ts, per unit depth in and out of the board. Okay, so we've established what it is we're trying to do in this problem. Let's talk about our approach. Okay, what we're going to do here, there's a lot of different aspects, but we know the general theme, which is we're going to look up correlations for the various things we're looking for, either the thicknesses of our boundary layers, or we're going to need H or shear stress. So we'll look up correlations for thickness, for local, for average, both convection coefficients, that'd be the shear stress at the surface locally and the shear stress at the surface averaged over the whole plate. And then we're going to use those correlations in order to find things of interest like Q double prime, Q prime, as well as, the total drag. Okay, so let's go ahead and do that in the analysis portion of our problem. We're going to just go A, B, C. We'll start with A. We're asked to find the thickness of the momentum and thermal boundary layer. Okay, turning to the best resource I found in the book is table 7.7 at the very end of chapter 7, which tells you every correlation, not every correlation, but the most useful ones you can find in chapter 7. Okay, and when we do that, we can get a correlation for the thickness of our momentum boundary layer, which is del over x is equal to 5 times the local Reynolds number raised to the minus 1/2. And that brings us to the issue of, oh man, we need the Reynolds number. Realizing all of these are evaluated at x equals L, that means we need to find the Reynolds number at x equals L. Well, remember, the Reynolds number is equal to our density times U infinity divided by our kinematic viscosity. Okay, so now we can look up our various parameters in table A5. Okay, so table A5 is for engine oil, because we need these properties if we're going to calculate the Reynolds number. Okay, and so our properties of interest are density, which is equal to 864 kilograms per meters cubed. We also need the kinematic viscosity, which is 86.1 times 10 to the negative 6th. That is meters squared per second. We're going to need the thermal conductivity for the Nusselt number, that's 0.140 units of watts per meter Kelvin. And the Prandtl number we're going to need also to find the Nusselt number, that is 1081. Now, all of these were evaluated at the film temperature, which is the average temperature between our surface, Ts, and the temperature of our fluid, T infinity. So 20 and 100 added together divided by 2 gives a film temperature of 333 Kelvin, because the table is organized by Kelvin, not degrees Celsius. So looking up our values and plugging them in to our Reynolds number calculation gives us a Reynolds number of 1,161. It is worth noting that is laminar flow. So when we're looking for correlations, we need laminar flow. All right, in fact, let's list the things we've already discovered. We know that we have laminar flow, that it's a flat plate. We know it's external flow. There is no mention of any other geometry, so we're assuming that the boundary layer is allowed to grow without any interference. We also know it's forced. Pressure-driven flow, we have a U infinity approaching. So we know external flow is chapter 7, all of which are forced, and then flat plate is the first few sections. And laminar identifies exactly what correlation we should use. So going there, I guess let's finish our train of thought up here. We already established an equation for the momentum thickness. So solving for that, we have x, which we'll now leave as L, times 5, times the Reynolds number at L raised to the minus 1/2. Okay, not plugging in numbers here, just evaluating the equation. We are given 0.147 meters. All right, so that is the thickness of our momentum boundary layer, or our velocity boundary layer at x equals L. But now, what about the thickness of our thermal boundary layer? Well, you'll remember that these two thicknesses are related by the Prandtl number, but not just specifically by the Prandtl number. We know from table 7.7, equation 7.24, where this, by the way, was equation 7.19. So equation 7.4 tells us that the thermal boundary layer is equal to the thickness of the momentum boundary layer times the Prandtl number raised to the minus 1/3. Well, engine oil has a huge Prandtl number. Where did I put that? Here we go. 1,081, where most gases are about 1. So plugging in that large number here and solving for our thickness, we get a value of 0.0143 meters, which is an order of magnitude smaller. Very interesting. Okay, so we have solved for the thickness of our momentum and thermal boundary layer. Now let's move on to our actual heat transfer. So we're asked to find the flux, the heat flux, and the shear stress at x equals L. So again, we have laminar flow, flat plate, external, forced. Going to our book, we can find a correlation that tells us the local Nusselt number for those specific conditions, and that is given by this equation right here, 0.332 times the local Reynolds number to the 1/2 times the Prandtl number of our fluid to the 1/3. Remembering that the local Nusselt number is equal to our local convection coefficient times our position x divided by the thermal conductivity of our fluid. Okay, well, this is all done at x equals L, or locally at the trailing edge of the plate. So using our Reynolds number we evaluated here, we know our Prandtl number, we can find our local Nusselt number. And rearranging using x equals L, we can find what h of x is. And when we do all of that, we get an h of x of 16.25 times watts per meter squared Kelvin. Now, remember, we're not trying to find h, we're trying to find heat flux. But the reason we found h was because for convection, heat flux is just equal to our heat transfer coefficient times the difference in temperature. Well, we already solved what h was. We're using our local here because we're looking for a heat flux, which would be at a specific location, x equals L. So plugging in our h here, and we know Ts and T infinity, we are going to get a value of minus 1300 watts per meter squared. That's a negative because the heat flux is actually going into our surface. When we derived this equation, we assumed it was going out. Okay, now we also need to know the shear stress. Well, we can use equation 7.20, which tells us that the local coefficient of friction, our non-dimensional shear stress, is equal to 0.664 times the local Reynolds number to the minus 1/2. Okay, and this is going to be equal to the shear stress divided by density times U infinity squared over 2. So you see right here is the value we're after, the shear stress. And all we need to do is plug in our local Reynolds number, 1161, and we know density and U infinity squared. So we can solve for our local shear stress at x equals L, and we get a value of 0.0842, and that will be units of newtons per meter squared, as it is a stress. Okay, moving on to part C. So that was part B. Now we have the last part, part C. We're asked to find the drag per unit depth and the heat transfer per unit depth. Well, the drag per unit depth would just be equal to the local shear stress averaged over the entire plate multiplied by the area that shear stress is acting over. Well, that would be the length of the plate, but remember we have the top and the bottom, so we need to include both lengths, 2L, this surface and that surface. Okay, now this, our average shear stress, we can compute using equation 7.29. To save space, I'm not going to write that out explicitly. Just know that it looks very similar to this one with a different constant, 1.328. So when we plug in those, then we get 0.337 newtons per meter, since we've now multiplied our shear stress by a length. Okay, finally, the heat transfer from the entire plate is going to be our average convection coefficient over the entire surface times our area, in this case just a length. Again, that is 2 times this distance because we have heat transfer from the top and from the bottom surface. Okay, multiplied by our temperature difference, Ts minus T infinity. Again, Ts is smaller than T infinity, so this will be a negative number. Well, you can, in this case, do two different things. You can look up a correlation for the average Nusselt number, which from table 7.7 you find is equal to 0.664 times the Reynolds number at L to the 1/2. Because remember, we're looking for the average value over this entire surface. So we plug in an x of L for our average, or the place that we're averaging up to, times the Prandtl number to 1/3. Which if you compare to this equation, you see that the average Nusselt number is just double the local Nusselt number. So when we do all of this, then we can actually find that the average convection coefficient would just be double the local convection coefficient. And we already found our local convection coefficient, so we know the value of the average convection coefficient, which would be 32.5 watts per meter squared Kelvin. So plugging in our h bar here, we know L and our delta T. We can actually compute our Q prime now, which would be minus 5,200 watts per meter. Okay, and the last part of our problem is we always add a little bit of discussion, which in this case, I think the most interesting takeaway is the very huge difference between our momentum and thermal boundary layer thickness, which we often see with engine oil, which has a large, very large Prandtl number here, 1,000, compared to a value of 1 that we usually have for gas. Okay, that's our problem. Thank you for watching.